Here's a question. You got several lists, each one already sorted, and you want a single sorted list out. How would you do it? We've got 3 lists today. Every one climbs upward on its own. The answer has to climb upward too. So where do we start? Look at what we're given. The first list is 1, 4, 5. The second is 1, 3, 4. The third is 2, 6. Each list is sorted, but they overlap. Both the first and second list open with a 1. That overlap is going to matter. We want them fused into one sorted chain. 1, 1, 2, 3, 4, 4, 5, 6. And we're linking real nodes, not copying numbers. The output is a linked list, stitched together from these existing pieces. The lists can run long too, up to 10,000 nodes in total. So whatever we cook up has to scale, not just work on a toy. Let's reason through the plain way first. To choose the very first node of the answer, where can it possibly come from? It has to be the smallest of the 3 front nodes. So we peek at all 3 heads. 1, 1, 2. Smallest is 1. We take it. Both the first and second lists start with 1, so pick either. Say the first. The first list steps forward to 4. The 3 heads are now 4, 1, 2. We peek again, take the smallest. That smallest is 1 from the second list. Take it, the second list steps to 3. The heads become 4, 3, 2. Feel the rhythm? Every single step, we rescan all the heads to find the minimum. That rescan is the whole cost. 3 lists feels harmless, but with 2 lists and n nodes total, that's n rescans of k heads each, n times k work. So as the lists grow, that k per step scan drags everything down. We need finding the smallest to be cheap. Let's turn this around. The slow part is hunting for the smallest head, over and over and over. What do we wish we already had? Some helper that keeps all the heads organized, and just hands us the smallest, no searching. That's a min heap. Picture hospital triage. The most urgent patient is always right at the front. No scanning the waiting room. We drop the front node of each list into the heap. The heap floats the smallest value up to the top all by itself. Pop the top. That node joins our answer. Then we push its next node, from the same list, back into the heap. The heap quietly resorts. Smallest on top again. Pop, push the follower, and keep going until it's empty. Let me say that again. The heap always holds exactly the current front of each list. Pop one out, push its replacement in. You might be tempted to pour every node from every list into the heap at once. Don't. Only 1 node per list lives in there. So the heap stays tiny at most k nodes. The search shrinks from scanning k heads to a single quick pop. But wait, how does the heap compare 2 linked list nodes? It can't, really. On a tie it tries and Python throws an error. So we store a little bundle. The value first for ordering, then a unique counter to break ties, then the node itself. The rule is simple. Compare by value, and when values tie fall back to the counter, the node never gets compared. Let's trace it for real. First we seed the heap. We push the head of each list. Values 1, 1, 2 go in. The heap arranges itself so the smallest sits on top. Right now the top is a 1. Which one? The bundle tells us it's from the first list. Pop it off the top. Link that node onto our answer. The answer begins with 1. Now push its successor. The first list's next node is 4. 4 goes into the heap. The heap resettles. The new top is value 1, this time from the second list. Pop it. Link it on. The answer reads 1, 1. Then push its next, which is 3. The smallest now is 2 from the third list. Pop it, link it on. The answer is 1, 1, 2. Push 2's follower 6. The heap holds 4, 3, and 6. The smallest is 3. Pop the 3 from the second list. Link it. The answer reads 1, 1, 2, 3. Then push its next, a 4. Now the heap holds 4, 4, and 6. 2 4s tied at the top. The counter quietly breaks the tie for us. Pop 1 4 from the first list. Link it on. The answer adds a 4. Push its next 5. The other 4 still waits. Pop it from the second list. That list is now exhausted, so nothing gets pushed. Pop 5 from the first list. Link it. The first list ends here, so there's nothing to push. The answer adds 5. Only 6 remains. Pop it, link it on. Its list ends too. The answer adds 6. The heap is empty now, so we stop. The final answer is 1, 1, 2, 3, 4, 4, 5, 6. Fully sorted. And look, we never once rescanned all the heads. The heap surfaced the smallest each time, in one quick step. Now the awkward cases, because hard problems love them. What if the input is completely empty, no lists at all? We seed by walking each list's head. With no lists at all, there's simply nothing to push. The heap starts empty. An empty heap means we never enter the loop. We just return nothing, right away. No crash, no special branch needed. Second case, one list, but it's empty. A single list holding no nodes at all. Its head is nothing, so we skip it while seeding. The heap stays empty again, and we return nothing. That's why seeding has to check each head before pushing. Skip the empties, or we'd shove a null in and break the compare. Notice what changed. We stopped rescanning the heads entirely. The heap remembers every candidate and surfaces the smallest in one step. Each node gets pushed once and popped once. A heap of size k costs log k per move, so the time grows with the total nodes times log k. And the memory. The heap never holds more than one node per list, so the extra space grows with k, the number of lists. Remember the core loop. Pop the smallest, link it onto the answer, then push that node's next. Repeat until the heap is empty. Remember the entry shape. Value first so it orders correctly, a counter second to break ties, then the node. Watch out for ties. Without that counter, Python compares the nodes themselves and crashes. The counter is not optional. Watch out for empty lists. Check each head before seeding, and use a dummy head so the empty answer falls out cleanly. Time to write it. We pull in heap, start an empty heap, and a counter for tie breaking. We seed the heap by walking each list and pushing its head, but only when that head actually exists. A dummy head gives the answer somewhere to attach, and tail is the pointer we keep extending. While the heap has anything, we pop the smallest bundle, ignore the counter, and link that node onto the tail. If the popped node has a follower, we push it back in. At the end we hand back the real list, skipping the dummy. And that's the pattern. A heap that always hands you the smallest. You'll reach for this anytime you're merging sorted streams.